Welcome back. In this video, we'll begin programming our robot and be exploring useful tools and classes you can utilize to go above and beyond. Now, to begin, we'll need to create our main OpMode class. Under Java, right-click on org.firstinspires.ftc.teamcode. Under New, select Package. I'll name this OpModes. Now right-click on OpModes, and under New, select Java class. You can name this whatever you like, but I'm going to go with Test Drive. Now, at the top, above the class header, type in @teleop. And between the class name and the squiggly brace, type in extends linear OpMode. Now, when it errors, go ahead and hover over it and hit Implement Methods. The first part to coding any robot is the hardware mapping class. It handles everything hardware, from adding motors and servos to retrieving controller variables. Because it's so integral to everything in the robot, we'll make this class the parent to everything. That way, everywhere in the code, we can move motors, read controller button presses, and more. Okay, to begin, right-click on the org.firstinspires.ftc.teamcode package, and under New, select Java class. Because it's integral to the whole of the robot, we'll name this class Robot. Go ahead and add it to Git. Let's begin by defining some variables that we will use throughout the project. We'll need the robot's op mode, so public volatile linear op mode op. We'll also need our controllers, so add two gamepad objects. Public volatile gamepad joy1, joy2. We'll also need our motors, so add the following list. Public volatile hashmap. Inside of the greater than less than signs, type in string, DC motor. And then motors equals new hashmap. And then we'll need a list for servos as well. Public volatile hashmap string servo. Servos equals new hashmap. Now, if it errors, don't worry. Go ahead and hover over it and import it. Now, let's take a look at what we have so far. Each op mode has controllers 1 and 2. We have a list for motors, and we have a list for servos. Now that we have these variables in place, we can begin using them. But first, we'll need to set the controllers and the op mode so we can handle input. We do that using a constructor. Constructors are basically bits of code that run when an object is created. In this case, each time an op mode is selected. Go ahead and write out robot, 2 parentheses, inside of it, linear op mode, op, and then 2 squiggly braces. This is a constructor. Inside of it, we can define the variables we set above. You may notice we pass in an op mode. That's because this itself is not an op mode, but simply guides it. So we'll need to firstly define the op variable. Type in this.op equals op. What it's doing is it's getting the op variable from the class and then setting it to the op variable in the constructor. Then we can use the op mode and access the controllers. Type in this.joy1 equals op.gamepad1 and this.joy2 equals op.gamepad2. Now, there are 2 more variables that we can include, but these are purely optional. We can have one list for color sensors and one for touch sensors. If you have these, go ahead and follow with me. Public volatile hashmap string, color sensor, color sensors equals new hashmap. And then public volatile hashmap string digital channel, this is for touch sensor. Touch sensors equals new hash map. Now that we define the controllers, you may be wondering how we'll add motors, servos, and sensors. For these, we'll need special standalone methods to handle them, since we won't be directly adding them in this class. To add motors, create the method public void add motor. Inside of the parentheses, write out string motor name, and then 2 squiggly braces. Now, if you're wondering, this string bit is your hardware's ID. You'll set these later down when configuring your robot in the app, as well as a list here in the code. Inside of the code, add a try-catch statement, which basically handles errors. Inside of the catch block, type in exception E. Now, inside of the try block, write out this.motors.put motor name op.hardwaremap.dcmotor.get motor name. This is adding the motor to the list. Now, also do op.hardwaremap.dcmotor.get motor name .setZeroPowerBehavior dcmotor.zeroPowerBehavior.break. This will grab the motor with the ID from the op mode's hardware map and add it to the motor list for easy access. If, for say, you improperly defined a motor ID, an error will be thrown, and that's what the catch block is for. Inside of it, we'll use telemetry. Telemetry is basically how you view the robot's current status on the app. Any warnings, errors, or statuses will be shown there. Follow along. op.telemetry.addData string error while adding motor, and then comma E. Then op.telemetry.update. Now, to make sure nothing goes wrong, also type in op.request opmode stop. At the end, we tell the op mode to stop because we don't want anything to happen to the robot that could physically mess it up. The process for servos is pretty similar. Go ahead and follow with me. Public void add servo string servo name, then 2 squiggly braces. Inside of it, put another try catch block. Catch will be exception E. Now in the try statement, put this.servos.put servo name op.hardwaremap.servo.get servo name. And then in the catch statement, put the same thing as above, except this time instead of saying error while adding motor, make it error while adding servo. If you're also planning on adding sensors, pause here and look at this code. Now that we have the main robot class, we'll need a subclass to handle tasks pertinent to the robot, like driving, moving arms, etc. Right-click on the robot class and select New Java Class. You can name it anything, but I'm going to name it Very Cool Robot. Once you have the class made, we'll need to make it inherit the parent class robot, so it has easy access to the motor lists and controllers. At the top of the class, between the class name and the squiggly brace, type in extends robot. Very Cool Robot is now a child of the robot class. However, you may notice the squiggly red error line underneath the class header. Hover over it and select Create Constructor Matching Super. It will automatically create the constructor so the linear op mode requirement is fulfilled. Go ahead and set it to public as well. Now that the class is ready, let's begin defining our variables once more. Remember how I mentioned we would need to define the motor's IDs in the code? This is where we'll put them. We'll need one for each motor on our drivetrain, so for our front left, we'll do public final string front left ID equals FLM. And then we'll also need one for the back left motor, so back left ID, and then we'll call that one BLM. We'll need one for the front right motor, and we'll call that FRM. And we'll need one for the back right motor, so we'll call that BRM. There we go. Now that we have our motor IDs, we'll need to add the motors to the list. In the constructor, after super, add all of the motors by calling the add motor method we defined in the robot class 4 times for each one. So add motor, front left ID, add motor, back left ID, add motor, front right ID, and then add motor, back right ID. Back right ID. Now that our motors are defined, we can begin adding the code to drive the robot. Let's create a method to handle it. We'll call it public void start drive with controller. And then inside of the parentheses, we'll pass along the parameter final gamepad joy. Inside of it, we'll define a thread. A thread is essentially a bit of code that runs simultaneously with other bits of code. Calling the method repeatedly in a loop over and over would be a waste of time, and if one bit lags, the entire robot will halt with it. So running it separately from the code in its own little sandbox is essential, so nothing bogs the rest of the robot down. In the method, write out thread drive thread equals new thread. Inside of the parentheses, write out new runnable, and it should autocomplete the run method. At the end, type out driveThread.start. The run method that appears is your sandbox. Anything that runs in it will be run simultaneously with your code. Now we can do the fun stuff. Let's get the robot to move when we use our controller. First, define the speed variable. I'll set it to 0.9, but you can set it to whatever you like. Within boundaries, of course. So float speed equals 0.9 f. Now, create a while loop. We'll need to make sure code is only run while the robot is active. So while op.opmode is active, and then 2 squiggly braces. Now lastly, we need to move the motors. So firstly, motors.get front right ID dot set power speed times minus joy dot right stick y minus joy dot right stick x. Then motors dot get front left ID dot set power speed times negative joy dot right stick y plus joy dot right stick x. And now all we have to do is copy these and make this back right ID and back left ID. What this is doing is multiplying the speed to how far your controller's right joystick is turned in the X and Y axis, and then setting the motor to it. In this example, the back motors mirror the front motors. Now, before we go back to our teleop class and finish, there is one more list that the robot class will need to store: your threads. Currently, we keep our thread variable inside of the method, meaning that if we want to stop it, it would be impossible. To get around this, go back to your robot class, and we'll define a new list at the top. So, public volatile hashmap string thread, and we'll call it threads, and it will equal a new hashmap. There we go. And to create the method to add a thread to the list, go ahead and go to the bottom and make a public void add thread, and then pass in thread, and then we'll call it thread object with 2 squiggly braces. And now, if thread object does not equal null, try to this.threads.put thread object.name, .getName, and then thread object. And in the catch block, we'll catch exception E, and we'll log op.telemetry.addData error while adding thread, and then comma E. and then we'll just have to update it. So up.telemetry.update. Now head back to your driving method, and right before we start it, do add thread, drive thread. And there we go. We can now add threads whenever we create them. That way we can have more easy control over how our robot moves. Now, all of what we've done is great, but the app still won't show it under teleop. And that's because we need to go back to the test drive class and call the method. So under op modes, go back to test drive. To begin, at the top of the class, write public, the name of your robot, so very cool robot for me. Not the robot class, but the name of the child. And then we'll name the variable robot. And then over here, in the method, run robot equals new very cool robot. And then we'll pass in this. Because it wants to take in an op mode, and this is an op mode, it will work. So each op mode is, at its core, a series of steps. 1, wait for the play button to be pressed. And we can do this by using the wait for start method. Then we can call our methods. So in this case, we only have one, robot.start drive with controller. And then we can pass in robot.joy1. Then we wait for the stop button to be pressed. So while op mode is active with empty body, and then all we have to do now is stop all the threads. And we can use a for loop for this. So for string s and robot.threads.keyset. Inside of it, we'll put a try catch block. And we'll catch an exception E. In the try block, write robot.threads.getS.interrupt. And what this is doing is it's stopping the thread immediately. Nothing else gets done, no matter what. And we'll leave the catch block empty for now. You're done. Your robot can now drive with the controller. Now that manual control is done, you might be wondering how to tackle autonomous functions. There are multiple ways of tackling it, but in the end, it's usually a mixture of all of them. Now, autonomous is similar to the way the teleop test drive class works, but instead of reading controller inputs, we use pre-recorded instructions, sensors, encoder inputs, as well as AI output. To start coding an autonomous function, we'll need to create a new op mode. Let's create 2 packages in the op mode folder, one to put our manual op modes, and one to put our autonomous op modes. So right-click on op modes, create a new package called teleop. Right-click on op modes again, create a new package, this time called autonomous. Stick test drive and teleop, refactor. Now under autonomous, create a new class called autonRobot, or whatever you like. Hit add to get, and now extend the class to linear op mode, and instead of at teleop at the top, make sure it's at autonomous. Now hover over the class header and implement methods. Also, create a new very cool robot at the top. So very cool robot, and then robot equals new very cool robot. And pass in this. Now, this looks very similar to the teleop class from the beginning, because at its core, we're doing the same thing, calling a list of instructions in order. The only difference is the instructions are now entirely pre-made, like move forward, wait for color sensor to see red, or move towards poster when AI detects it. There are several instruction methods that every robot has. Firstly, the sleep method. This method stops the robot for a predetermined amount of time. Maybe you need to wait for a game item to be placed, or maybe you need to add a small amount of time between movements. Whatever you'll be doing in Auton, I guarantee you'll need this eventually. Let's head back to our very cool robot class and create a new method. I'll call it sleep. We'll also pass in a long called milliseconds. Longs are basically integers that can store way longer numbers. Now we need to pause the robot. We'll first need to get the current time in milliseconds, which is accessed through system.current time milliseconds. This returns an extremely long number, representing the current time in milliseconds. Whenever we want to add milliseconds to it, we are basically setting a time in the future. Knowing this, we can take the time we want to wait, add it to the current time in the variable, and then wait until the current time supersedes this. We've then paused for that amount of time. So, inside of sleep, define the variable time to end. It will be of type long, and it will equal system.currentTime milliseconds plus the milliseconds we passed in. This creates a timestamp in the future where we want to stop. Now, create a while loop, which runs until the future timestamp is no longer in the future. So while time to end is greater than system.currentTime milliseconds, we wait. We'll also need to check to make sure we didn't press the stop button. So and op.opmode is active. We'll keep the body empty. And just like that, we have a sleep function. To call this in our autonomous op mode, go back to your autonomous class and say wait for start, and then robot.sleep for 2 seconds, so 2000. Alright, so now that we have a sleep function, you may be wondering how we get the robot to move and turn. There are multiple ways of handling movement. The simple way is just guesstimating time, plugging it in, and hoping it goes the distance you want. The more complicated one is where we use encoders to determine how far we'll need to go in one movement. Now, using time is as simple as the sleep method, but instead of doing nothing in the while loop, you can set each motor's power to a constant variable. With encoders, it's a bit more difficult. Encoders in most motors convert the movement of the motor and translate it into counts. Counts that can then be translated into inches and vice versa, using a little bit of math. Let's go back to the child robot class and define a few variables. At the top, say protected, final, static, double, wheel diameter. And for me, I'll set it to 3. This is the diameter of your wheels in inches. The second one will be protected, final, static, double, counts per revolution. I'll set this to 288. Now, you'll find the counts per revolution usually on the manufacturer's store page or in a user guide. The last one is protected, final, static, double, gear reduction. I'll set this to 1, but this will be important if you're using a reduction gearbox. So if it's 2 to 1, then it would be 2 times, for instance. Okay, now we can take these variables and calculate them into counts per inch. Protected, final, static, double, counts per inch equals, in parentheses, counts per revolution multiplied by gear reduction divided by, in parentheses, wheel diameter times math.pi. And there we go. We have our counts per inch, and we can use this along with the encoder to determine how far to move. Okay, now we need to create a new method for moving with inches. I'll go public void move with encoder. In the body, write for string s motors.keyset motors.getS.setMode DC motor.stop and reset encoder. And then secondly, motors.getS.setMode DC motor.runMode.run to position. This will recalibrate our motors to make sure we start fresh. And now we need to pass in inches into the method. So int inches. We can then take inches and calculate it into counts, which we can then tell the motor to move. So int counts equals inches multiplied by, in parentheses, int counts per inch. We can now take this and set the new position for each motor to the old one plus the counts. So for example, motors.get front left ID .set target position motors.get front left ID .get current position plus counts. I'm going to do this for the rest of them. And there we go. We have all of our motors moving for that amount of time. Now we need to set the speed for each motor through a method of sorts. Let's go down to the bottom and say public void set drivetrain speed. And you'll put in a double speed. In the body, for each motor in your drivetrain, set the power. So motors.get front left ID dot set power speed. And then you can do the same for the other three. So back left ID, front right ID, and back right ID. And there we go. We now have an easy way to set the speed. So right here, say set drivetrain speed, and for now we'll set it to 1. You can change that to whatever you like and whatever speed you want. You can even pass it in to the method, but for now we're just going to set it to 1. Now what we have to do is add a while loop that waits while the op mode is active and while each motor is running. So while op mode is active and motors.get, I'll choose front left ID is busy, but you should probably do this for every single motor. But for now, I'm just going to do the front left motor. And then we can just wait. So while each motor is moving, we'll wait. And then once it's done, we can then set drivetrain speed to 0. Now go back to your autonomous op mode. And after robot.sleep, just say robot.move with encoder. And I'll set the distance to 12 inches, so a foot. You now have an auton that can move forward, sleep, and soon turn. Another popular tool used in autonomous robots is called an IMU, or Inertial Measurement Unit. They are similar to gyros in the way they detect movement in all axes. They are used for turning and pathfinding, among other things. It's too complicated to go fully in depth here, but this page by STEM Robotics has a ton of useful methods for you to look at. In the run function of the op mode, they include a simple object detection system, which uses a touch sensor. If the touch sensor is pressed, it'll turn 90 degrees. Towards the bottom, it also has a general purpose turning function, which can be very useful. So here, you'll see that it takes in the degrees and the power, so the speed, and then it'll reset the angle, and then it'll slowly turn depending on which direction it's currently in. So it'll set, and then it'll move it, and it'll wait until it's gotten to this correct angle. And then once it's done, it sets the power to off and waits. Before we finish this part, I'll give you a quick look at two common object recognition algorithms, called Vuforia and TensorFlow. They both tackle the problem of detecting blocks, especially with certain images, but are different in how they go about it. Vuforia is quick and accurate, but requires a good detailed look at a target and can only recognize 2D images. TensorFlow, on the other hand, is way slower and more resource intensive, but can recognize full 3D objects. I'll make sure to link some of these pages in the description. In the next part of the series, we'll take a look at how to get the code off the laptop and onto your robot.